Welcome to this video, and in this video we look at the repeated eigenvalues in an eigenvalue eigenvector problem. We look at the repeated eigenvalues. So in some cases, when you evaluate the eigenvalues of a matrix A, some of the eigenvalues will be repeated, and the problem of determination of the eigenvectors will take a different route because you end up with the same equation as opposed to a set of simultaneous equations of which you can obtain the solutions for the eigenvectors. I will illustrate this with an example. We have to determine the eigenvalues and the eigenvectors of the matrix A given the matrix equation AX is equals to lambda X, where the matrix A is 3, -3, 2, -1, 5, -2, -1, 3, 0. So this is our matrix A. And we determine the eigenvalues and the eigenvectors of the matrix A. So the eigenvalues will be obtained by solving for the characteristic equation lambda I minus A determinant is equals to 0. In this case, I will be an identity matrix of order 3 because A is a 3 by 3 matrix, and therefore we will have lambda minus 3 minus 3. So this becomes positive 3, then -2. We'll have this as 1, lambda minus 5, then 2, 1, minus 3, lambda, determinant equated to 0. This one will lead to lambda minus 3. This will lead to lambda minus 3 into lambda squared minus 5 lambda plus 6 minus 3 into lambda minus 2 minus 2 into, and we get minus 3 minus lambda minus 5 is equals to 0. We expand this to get lambda cubed minus 8 lambda squared plus 21 lambda then minus 18, then we get this to be minus 3 lambda plus 6. Then we have plus 2 lambda, and then minus 4 is equals to 0. We expand this, then we'll get lambda cubed minus 8 lambda squared plus 20 lambda minus 16 is equals to 0. So this is our characteristic equation. If you solve for the roots of this characteristic equation, you'll get lambda 1 to be equal to 4, lambda 2 to be equal to lambda 3, which is 2. And this is what we are calling the repeated roots or the repeated eigenvalues. which changes the problem of eigenvector determination. For lambda 1 is equals to 4, then we can obtain our matrix equation as 3 minus 3, 2, negative 1, 5, minus 2, minus 1, 3, 0. That's our matrix A, multiplied by x, which is x1, x2, x3, will be equal to 4 into x1, x2, x3. We can proceed and write. So we have our 3 minus 3, 2, negative 1, 5, minus 2. And we have minus 1, 3, 0, multiplied by x1, x2, x3 will be equal to 4 into x1, x2, x3. From this, we can write 3x1 minus 3x2 plus 2x3 is equals to 4x1, from which we can have x1 plus 3x2 minus 2x3 is equals to 0. Call that equation 1. Then you can have minus x1 plus 5x2 minus 2x3 is equals to 4x2, from which you can write x1 minus x2 plus 2x3 is equals to 0. You can call that equation 2. Lastly, we'll have minus x1 plus 3x2 is equals to 4x3, from which we can write x1 minus 3x2 plus 4x3 is equals to 0. We can call that equation 3. Then we solve for x1, x2, and x3 as follows. If I take equations 1 and 2, if I take equation 1 and add to equation 2, I will eliminate x3. Because this is negative, this is positive. If you add the 2, then you'll get 2x1, then plus 2x2. In this case, will be equal to 0, and therefore x2 will be negative x1. Next, we can take equations 1 and 3, we add them. We take equation 1, we add to equation 3. We take equation 1 and add to equation 3. We eliminate x3. So we take this, you eliminate x2, so this is negative, this positive 3, this is negative 3. So if you add the 2, you'll get 2x1 plus 2x3 will be equal to 0, where x3 will also be equal to negative x1. Then we can take the simplest values. If x1 is equals to 1, x2 is negative x1, which is negative 1, and x3 is also negative x1, which is negative 1. And therefore, our first eigenvector will be 1, negative 1, negative 1. That is the first eigenvector. For lambda 2, is equals to lambda 3, which is 2. Then our matrix equation becomes 3 minus 3, 2, negative 1, 5, minus 2, negative 1, 3, 0. We multiply this with x1 all the way to x3. We equate this to 2 into x1, x2, x3. Then we form the following set of simultaneous equations. The first one, 3x1 minus 3x2 plus 2x3 will be equal to 2x1, from which we can write x1 minus 3x2 plus 2x3 is equals to 0. That becomes equation 1. The second set will give us minus x1 plus 5x2 minus 2x3 is equals to 2x2. Then we take all these terms to the right, we'll get x1 minus 3x2 plus 2x3, which will be equal to 0. And equation 1 and 2, you notice they're the same equation. Lastly, minus x1 plus 3x2 will be equal to 2x3, from which you get x1 minus 3x2 plus 2x3 is equals to 0, and this is supposed to be our equation 3. But again, a closer look at equation 1, 2, 3, it is the same set of equation, and therefore we cannot obtain the solutions of 3 variables from only one equation. We expect 3 sets of simultaneous equations to be able to determine the values of x1, x2, and x3. If this happens, then we carry out the analysis of the eigenvectors as follows. We can write x1 in terms of x2 and x3 as follows. x1 is equals to 3x2 plus 2x3. Then we can take arbitrary values of x2 and x3 and say, if x2 is equals to beta and x3 is equals to alpha, where beta and alpha are constants, these are constants, then we can write x1 as follows. x1 will be equal to 3 beta plus 2 alpha. Then x2 is beta and x3 is alpha, from which we can write the vector x1, x2, x3 is equals to a matrix multiplied by beta plus a matrix multiplied by alpha. So x1 is 3 beta and 2 alpha. Notice when you make x1 the subject of the formula, x3 will be negative. Sorry for that. So this is supposed to be negative. And therefore, this is negative. So this will be negative. Then x2 is beta, that is 1 for beta and 0 for alpha. x3 is alpha, which is 0 for beta and 1 for alpha. Then we say if beta is equals to 1 and alpha is equals to 0, the simplest values, then we get the values of x1, x2 as follows. Our second eigenvector will be equal to, so if this is 0 and this is 1, we'll get the eigenvector 3, 1, 0. If beta is 0 and alpha is 1, if beta is 0 and alpha is 1, then our third eigenvector will be obtained as negative 2, 0, 1. And through this, We are able to determine the eigenvectors when the eigenvalue is repeated in a matrix equation. We have already determined the values of eigenvector 1, which was 1, negative 1, negative 1. Eigenvector 2 is the vector 3, 1, 0. So this is 3, 1, 0. And eigenvector 3 is negative 2, 0, 1. We said that we can obtain a transformation matrix P. We can obtain a transformation matrix P from the eigenvectors of the matrix A as P, which is eigenvector 1, 2, and 3. In our case, our matrix P will be 1, negative 1, negative 1, then 3, 1, 0, minus 2, 0, 1. And we said that under similarity transformation, the characteristic equation of the matrix A does not change, and hence the eigenvalues of the matrix A does not change. If we use P as our transformation matrix, then the A hat matrix will be given by P inverse AP, which will be negative, it will be 1. It will be 1, negative 1, negative 1, 3, 1, 0, minus 2, 0, 1, inverse, multiplied by the matrix A, which was 3, minus 3, 2, negative 1, 5, minus 2, negative 1, 3, 0, multiplied by matrix P, which is 1, negative 1, negative 1, 3, 1, 0, minus 2, 0, 1. If you evaluate this matrix computation, then the matrix A hat will be a diagonal matrix 4, 0, 0, 0, 2, 0, 0, 0, 2. And as you can see, under similarity transformation, if we use P obtained from the eigenvectors of the matrix A, the matrix A is transformed into diagonal form. And as you can see, the roots will be 4, 2, 2, which were our previous roots on the major diagonal here. And therefore, the characteristic equation of the matrix A will not change, since our characteristic equation will be obtained by lambda I minus A hat determinant is equals to 0, which will be lambda minus 4, 0, 0, 0, lambda minus 2, this is lambda minus 2, 0, 0, 0, lambda minus 2, determinant is equals to 0, which can give us lambda minus 4 into lambda minus 2 into lambda minus 2 is equals to 0, which will be the same characteristic we had as lambda cubed minus 8 lambda squared plus 20 lambda minus 16 is equals to 0. And therefore, under similarity transformation, the characteristic equation of the matrix A will not change, and hence its roots will not change, or the eigenvalues will not change. In number 2, the matrix is transformed into diagonal form with the roots appearing on the major diagonal. And that is my end. That is the end of my presentation on the repeated eigenvalue problem. Thank you for watching this video.